Hi guys, Professor Barber here. This lesson is titled Polynomial Functions and Their Graphs. In this lesson, we will study polynomial functions of any degree. Our goal is to develop sufficient conceptual understanding and technical skills to be able to solve polynomial functions of any degree. To that end, we will learn in this lesson how to graph polynomial functions by determining their shape near zeros and also their end behaviors. Upon successful completion of this lesson, you will 1. Be able to recognize polynomial functions. 2. Be able to graph basic polynomial functions. 3. Be able to apply the leading coefficients test and the end behaviors theorem to graph polynomial functions. 4. Be able to use zeros to graph polynomial functions. 5. Be able to determine the shape of a graph near zero. And 6. Be able to find local maxima and minima of polynomial functions. Roman numeral 1. Polynomial functions. A polynomial function of degree n is a function of the form p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... plus a sub 1 x plus a sub naught, where n is a non-negative integer and a sub n does not equal 0. The numbers a sub 0, a sub 1, a sub 2, ... all the way to a sub n are called coefficients. The number a sub naught is the constant coefficient or constant term. The number a sub n is the coefficient of the highest power, and it is called the leading coefficient. And the term a sub n x to the n is called the leading term. Roman numeral 2, end behavior and the leading term. The graphs of polynomial functions all have the characteristics of being both smooth and continuous. The term smooth means no cusps or sharp corners. The term continuous means there are no breaks or gaps. Let's look at the images of some polynomial functions. Note that each of these 5 polynomial graphs are smooth. That is, there's no sharp corners anywhere. Furthermore, if you were to put a pen or a pencil on any part of any graph, it would continue in both directions indefinitely. The arrows on the extreme ends mean that the graphs continue without end. Now let's look at some notation. X, arrow, infinity. This is read x approaches infinity, and that means x increases without bound. So consider a graph as you move on the x-axis towards the right, on and on and on. X, arrow, negative infinity. This is read x approaches negative infinity. This means x goes to negative infinity, and that x gets decreasing or increasingly smaller. That continues to the left without end. Continuing with end behavior. The end behavior of the polynomial p of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... plus a sub 1 x plus a sub 0 is determined by the degree n and the sign of the leading coefficient a sub n as indicated in the following graphs. Let's observe that the degree n is the highest degree present, not necessarily the first term that appears in the written expression of the polynomial function. Similarly, the SIGN of the leading coefficient a sub n, the leading coefficient is the number that's multiplied to the x of the highest degree and not necessarily the first term that appears. So, if the degree n is even, so it's 2, 4, 6, 8, and the leading coefficient is positive, then regardless of what happens near the origin, the end behavior is that both ends will eventually be going up. Now that doesn't mean that you can't have all kinds of funky little things in between, okay? Now, degree n is even and the leading coefficient is negative. That means both ends are down. Again, this could just be a simple parabola, but it could also have all kinds of curves in it as long as both ends end up going down. Now, if degree n is odd, so 3, 5, 7, how much ever, and the leading coefficient is positive, then as you move from the left to the right, the graph is going to be increasing. And so you might say extreme left end is down, extreme right end is up, and whatever happens in between. Okay, that's not what this tells us. This is in behavior. And finally, if the degree n is odd and the leading coefficient is negative, then as you move from the left to the right, the graph will end up decreasing, but that doesn't necessarily mean that it's going to be straight. It can have all kinds of, non-sharp corner cusp behavior in between. Roman numeral 3, zeros of polynomial functions. If p is a polynomial function, then c is called a zero of p if p evaluated at c equals 0. That is, the zeros of p are solutions of the polynomial equation p of x equals 0. Note that if p of c equals 0, then the graph of p has an x-intercept at x equals c. Let's visualize that. Let's look at a portion of a polynomial graph. So we'll have a graph that looks like it starts in the second quadrant, intersects the y-axis between the second and first quadrant, and then decreases hitting the x-axis and then going into the fourth quadrant. Let's suppose the point where the graph intersects the x-axis is C. What we have here is a solution. That is what is meant by P of C equals 0. For P a polynomial and C a real number, the following are equivalent statements. 1. C is a 0 of P. 2. X equals C is a solution of the equation P of x equals 0. 3. X minus C is a factor of P of x. And 4. C is an x-intercept of the graph of P. The intermediate value theorem. If P is a polynomial function and P of A and P of B have opposite signs, then there exists at least one value C between A and B for which P evaluated at C equals 0. Let's illustrate. I'll plot the point A in the first quadrant, and I will also plot B in the first quadrant, but some space to the right, and I will define a particular value in the first quadrant that corresponds to P of A, and another particular value in the fourth quadrant that corresponds to P of B. So if we were to graph this function that's smooth and continuous, notice the thing that this graph must do. It has to go through the x-axis. So the intermediate value theorem says if a function value goes from positive to negative, or likewise negative to positive, then there has to exist some c so that the function equals 0. Behavior of polynomial functions near 0 of multiplicity m. If c is a 0 of p and the corresponding factor x minus c occurs exactly m times in the complete factorization of the polynomial p, then we say that c has a 0 of multiplicity m. Think of it as x minus c to the m. M is the number of times it occurs. If the multiplicity m is odd, that is, it's to the 1, 3, 5, 7, then it crosses or intersects the x-intercept at c. So let's suppose we have x minus c cubed, and that's what our polynomial is equal to. Then at c, graph of the polynomial will go through that intersection. If the multiplicity m is even, then the graph does not cross it, but it remains tangent to it. So let's suppose we have p of x equals x minus c. Give me a nice even number. 28, ridiculous. It doesn't matter. But anyway, so we'll have a graph. If it occurs an even number of times, then the graph will touch it, or another way to say it is it is tangent to it, but it will not cross at that zero. Sketch the graphs of the following polynomial functions. A, p of x equals x minus 3 times x plus 2 times x minus 4. Let's list the information we can readily get off of the graph. First thing is that at the degree, x times x times x is 3, so we know that it is odd. The leading coefficient, x times x times x. The constant there is just 1, so we know that that's positive. That gives us our end behavior. That is, it is degree odd, so it's opposite directions. It's going to be increasing, so that gives us our end behavior. We got that done. Now let's list the zeros. This polynomial is nicely factored for us, so we know that we have x-intercepts at 3, -2, and 4. Let's label those on the graph. I'll mark -2, 3, and 4. Oh, and we've got one more piece of information we can readily get, and that's the y-intercept. And we get that by multiplying the constants together. -3 times 2 times -4. So negative and negative is positive. 6 times 4 is 24. So I'm just going to put a dot on the upper end of the x-axis and write 24. Now let's note that each of these zeros are multiplicity 1. X minus 3 is to the 1. X plus 2 is to the 1, and x minus 4 is to the 1. And the multiplicities theorem tells us that if it's raised to an odd power, the multiplicity, we go through. So we'll go through -2. Let's hit that y-intercept, come down, go through 3, go back up through 4, and we have a rough sketch of the polynomial function of degree 3. Part B, p of x equals -3x to the 4th plus 11x cubed plus 4x squared. This is a wonderful problem to let us review how to factor. And so looking at this, we see that it's a degree 4. So let's go ahead and write that down. It's degree 4. That's even. And the leading coefficient is negative, right? Because it's -3. So both ends, extreme ends, facing down. Not a whole lot of other information. Now we got to go back to factoring. I'm going to factor out a -x squared. Then -3x to the 4th divided by -x squared would be +3x squared. Factoring out a negative from the middle term, +11x cubed divided by -x squared would be -11x. And for the last term, 4x squared divided by -x squared would just be -4. We can factor that quadratic, so we have -x squared. And then we'll have, let's see, 3x times, and then x. We need a factor that'll give us a 4 for the last term and 11 in the middle. So the factors of 4 we have are 2 and 2 and 4 and 1. Let's stick with 4 and 1. We need to get large enough to 11, so I need 3 multiplied to 4, and the other remaining factor would be plus 1. Now, let's check our zeros. That's where this expression equals 0. So we will have zeros at x squared equals 0 would be 0. And let's go ahead and note that this is multiplicity 2 because it's x squared. And then we have a 0 of negative 1/3 and 1 of x equals 4. So let's mark these. We'll have the origin 0, 0. Let's go ahead and mark negative 1/3 and positive 4. Oh, and the y-intercept, by the way, we don't need to compute it because it's a function, and if x intersects the origin, then so does the y. And the interesting thing to remember is that at 0, it bounces. So we go from decreasing through 0, bounce right back up, go back through 4, and come back down. This gives you a general shape of what this graph would look like. Part C, p of x equals x cubed plus 2x squared minus 9x minus 18. A couple of things we can get right off by looking at this. One is that this is degree 3, or odd. And furthermore, the leading coefficient is 1, and 1 is a positive number, so the leading coefficient is positive. So we know that the extreme ends are continually increasing, so going downwards in quadrant 3, up in quadrant 1. The other thing we can get right off of it is the y-intercept, because that's the constant, so the y-intercept is going to be negative 18. Just pick a point towards the bottom of the y-axis and we'll mark it negative 18. Now to find the x-intercepts, we're going to have to factor that 4-term expression. Let's do it by grouping. So I'm going to say 0 is equal to, let's group x cubed plus 2x squared plus, let's group negative 9x minus 18. Then from the first grouping, we can factor out an x squared, and that will leave x plus 2. And from the second grouping, I'm going to factor out a negative 9, and that also gives us an x plus 2. The x plus 2 is what is common to both of them, so we can factor out the x plus 2 from the first terms of x squared times x plus 2, and x plus 2 from the second term of 9 times x plus 2. Then what remains is x squared minus 9. X squared minus 9 is a perfect square, so let's go ahead and write 0 equals x plus 2 times x plus 3 times x minus 3, and so the zeros from these factors are negative 2, negative 3, and positive 3. Let's mark those. I'll mark negative 3, negative 2, and 3. Let's note that each of the zeros went only to 1. So those were odd multiplicities. That tells us that the graph will go through those zeros. So starting from the end behavior in the third quadrant, go through negative 3, go through negative 2, go through the negative 18 y-intercept, go through the 3, and there is our graph. Roman numeral 4, local maxima and minima of polynomials. Presented as a graph with 3 smooth turning points. It increases starting in the fourth quadrant up into the second, smoothly turns and begins to decrease going through the origin, has a turning point in the third quadrant, increases again into the fourth quadrant, makes a quick turn, begins a decrease, and then continues to decrease indefinitely in the fourth quadrant. Now, looking at this graph, we have a high point associated with the value x equals negative 6. The corresponding function value is called a local max or local maxima, It is local because we only look right around that value, and in order to move from this high point, the only way that we can do this is to move down. So when the only possible alternative is to move down, we have a local max. Now we continue to decrease, and let's observe that at x equals 3, we have a low point on the graph. In order to budge from this point, the only way you can go is up in either direction, and that is how we describe a local min. Okay? We have another local max at, it looks like x equals 9. And again, in order to move from this local max, the only way that you can go is down. The set of all local minima and maxima on the graph of a function is called its local extrema. One more interesting thing, if p of x equals a polynomial such that it's a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 1 x plus a sub naught is a polynomial of degree n, then the graph has at most n minus 1 local extrema or turning points. So your parabola or your basic square function y equals x squared, observe that it has one turning point. This is also true for any degree. Let's look at the graph that's presented. We have 1, 2, 3 turning points, and with 3 turning points we get to conclude that the least possible degree of this polynomial graph is 4. Consider a polynomial function p of x. Suppose that the constant a sub naught equals 2, the leading coefficient a sub n equals 3, and the degree of p of x is 5. Determine which of the following graph best represents the polynomial described. So let's begin with the constant a sub naught equals 2. That means the graph has to intersect the y-axis in a positive, so it can be here, that's A, B, or D. So we have eliminated C and E as a possibility. The leading coefficient is a sub n equals 3, so the leading coefficient is positive. Leading coefficient is positive, and the degree is 5. That's odd, and so positive and odd means we need a behavior that is increasing from the first, second, third quadrant to the first, and so of the 3 remaining choices, graph D best fits that description.